Okay, so picking up from where we left off on the last video, I just want to separate those in case some people just want to come in and see me working through problem set 33 and 34. That's what we're going to do in this video, is problem set 33 and 34. Again, always going back and referencing these equations for Q that we talked about. So starting at the beginning. What is the difference between heat capacity, molar heat capacity, and specific heat capacity? Well, heat capacity just is a variable that relates the amount of heat something absorbs to the amount of temperature change that that thing experiences. So if we're just talking about an object, we just use a heat capacity. And the units are just, so this is for an object, and the units are just like kilojoules per degree Celsius. Says if I put in 5 kilojoules, that will change the temperature 1 degree Celsius of that object. Then we have molar heat capacity. Well, that's usually in like joules per gram degree Celsius. And just as a note, anytime I write kilojoules or joules, those are interchangeable, right? If it could be kilojoules per Celsius, it could be joules per Celsius. Those are essentially the same unit, just a different magnitude. So anyway, molar heat capacity, is joules per mole degree Celsius. In other words, if I'm just dealing with a substance that I could have different amounts of, then if my heat capacity was 5 joules per mole degree Celsius, then it takes 5 joules to raise the temperature of 1 mole 1 degree Celsius. And then lastly, specific heat capacity is just on a per gram basis. So the amount of heat it takes to raise 1 gram 1 degree Celsius. Okay, number 2, you're at the beach on a warm summer day. Your toes feel nice and cool swimming in the ocean. Then you walk barefoot into the ice cream stand and notice that the wet sand was much warmer than the ocean. Walking across the paved parking lot to your car, black asphalt was even hotter, almost as hot as the dry sand, and you vowed to never forget your flip-flops again. Resting one hand on your car for balance while you tried to wipe the dirt and sand from your feet was a big mistake. The metal was too hot to touch. Rank the 4 materials: water, wet sand, asphalt, and metal, in order of lowest to highest heat capacity, and explain your reasoning. All right, so all of these things are sitting out in the sun, and they've been sitting out in the sun for the same amount of time, and yet some of them they're different temperatures, right? So if I have a high heat capacity, that means that I have a high capacity to absorb heat without changing temperature. So things with a high heat capacity absorb heat and don't change temperature that much. So what's going to have the highest heat capacity? Well, the things that have not heated up. So the highest heat capacity, what they want order from lowest to highest. Okay, so lowest and highest. Well, the thing with the highest heat capacity is going to be the lowest temperature, so the water. The thing with the lowest heat capacity has the lowest capacity to absorb heat without changing temperature, so that's going to be the metal because it changed temperature a lot. It has a low capacity to absorb heat. And then they'll just go in order of how hot they were. So we get metal, asphalt, wet sand, and then water. All right. In an experiment, you scoop up a handful of sand on a very hot day at the beach. The sand happens to be that many grams exactly and 96.7 degrees Celsius. That's very hot. You quickly transferred the sand to 1.25 times 10 to the second grams of water. At that temperature, final temperature comes to 32.5. What's the specific heat capacity of the sand? All right, so what is the fundamental concept here? The fundamental concept is the first law of thermodynamics. What does the first law of thermodynamics say? It says that the total energy of the universe cannot change. Total change in energy of the universe has to be 0. So I take this hot sand and draw a little picture. I got my water. I take this hot sand and I dump the hot sand. This is my sand that I dumped in the water. Well, what's going to happen when you put hot sand in cold water? The heat is going to leave the sand and enter the water. So the sand is going to get colder, the water is going to get hotter. But where does the heat from the sand go? Into the water. Where does all of the heat from the sand go? All of the heat from the sand goes into the water. Okay? Energy can't be created or destroyed, so I know that the heat from the sand and the heat of the water have to add up to 0. Okay, how is that going to work? Well, it means that one of those Q's is going to have to be positive and one is going to have to be negative, but their magnitude is going to have to be exactly the same. I could subtract one over to the other side and say that the Q of the sand will be negative Q of the water. Okay, I could have subtracted sand over to the other side. It really doesn't matter. I could have left them on the same side. I'll still be able to solve the problem. So what does it mean for a Q to be negative? Well, that means that heat is leaving that thing. So for which of these Q's, Q sand or Q water, will the actual value be negative? In this case, it will be the Q sand because heat's leaving the sand. So Q sand will be negative. Some people get confused because they think that negative sign should go on the Q that is releasing heat. Okay? That's not true. That negative sign could go on either one. All it's saying that is that if let's say, for example, this is not true, but let's say, for example, the Q of the water ends up being negative, well, then we need to flip the sign because the Q of the sand will be positive. Okay? All this is saying is that the two need to have opposite signs. This is not saying the water's Q would be negative. We need to do the math, then we'll know if the water's Q is positive or negative. Okay, so I know that all of the heat from the sand goes into the water. Well, they didn't give me any heat values. They gave me masses, they gave me temperatures, they gave me heat capacities. Okay, so obviously I'm not just going to be able to plug in Q values here. What I'm going to need, what I'm going to need is I'm going to need to break down these Q values for Q sand and Q water. I need to break them down into variables that we can measure. Well, if you remember, in the last video, that's what we did. We created equations for Q and broke them down into variables that we can measure. Just going to move this down so it's more accessible. Okay, so the question I asked myself is, and this is literally the question I asked for every single one of these problems, Q of the sand. What's happening to the sand? If you asked a second grader, they might say that the sand is getting colder. Okay? Is it still sand at the end of the day? Yes. It's just sand at a different temperature. Well, we decided that if all you're doing is changing temperature, you're going to use a Q equals MC delta T. Okay? Now I could potentially use a Q equals C delta T. That's for an object. Is this an object? No, this is just a substance. It's sand. So I'm going to use Q equals MC delta T. So I'm literally just going to replace that in the equation with M, I'm going to use an S for sand, CS delta TS. Okay? That's going to equal negative. Now what's happening to the water? Well, again, if I ask a first grader, they might say the water's just getting warmer. It's still water. Okay? All it's doing is changing temperature. So I'm going to use an M water, C water, delta T water. Now you notice that I'm putting subscripts to specify what these variables are of, because otherwise people often mix up. They use the mass of the water and the specific heat of the sand, and you can't do that, right? If I'm calculating Q of the water, then I'm just using variables related to the water. Now at this point, the problem just became really easy, right? All I need to do is plug in the variables that I know. So, and then I'll be able to solve the variables that I don't know. So, what am I trying to solve for? I'm trying to solve for the specific heat capacity of silicon dioxide. All right. Remember, specific heat capacity we talked about before would be in joules per gram degree Celsius. So I need the mass of my sand, which is 200 grams. I'm looking for the specific heat capacity of my sand. Change in temperature of my sand. Well, it says that it started at 96.7 degrees Celsius and it's going to end at 32.5. So 32.5 minus 96.7. Remember, change is final minus initial. That's going to equal negative mass of my water. So they tell you 125 grams. Should have labeled this as degrees Celsius. And then specific heat of water is 4.184. Do they give that to you? Awesome, they do. And that's in joules per gram degree Celsius. and then change in temperature of my water. Now remember, if I put the sand in the water, the sand's going to cool down and the water's going to heat up until they're the same temperature. So my final temperature is the same, 32.5. My initial temperature is 15.2 degrees Celsius. Okay, so I can plug all this in my calculator. I'm going to do that. I'm also going to check with the key to try and make as few mistakes as possible. Okay, so over here I get that the Q of my water is 9047.9 joules. Now, is the Q of my water negative 9047.9 joules? No, it's positive, which makes sense because heat's going into the water. This negative sign is now saying, okay, if I want that to be equal to the Q of the sand over here, then I need to put a negative sign because the Q of the sand is going to be negative. Okay, that equals all of that stuff over there. So then I can finish the math. Let's see if I got the right answer. Yes. Okay, I got that the specific heat of the sand is going to equal 0.705 joules per gram degree Celsius. That is what the problem is asking me to solve for. All right, let's keep going. Number 3, B now. It says a 40-gram piece of gold at 76.2 degrees Celsius is dropped into 10 grams of water at 20 degrees Celsius. After a short time, both the gold and the water reach a stable temperature of 26.2 degrees Celsius. Use this information to calculate the specific heat of gold. Okay, very similar problem. We're trying to find the specific heat of gold. So again, we know that the change in energy is going to have to add up to 0. So then we know what are the different things exchanging heat here. Well, we've got gold, and we've got, what is it dropped into? Water. Those have to add up to 0. So Q of my gold equals negative Q of my water. And just to emphasize the fact, I could say negative Q of gold equals Q of water. It really does not matter where I put my negative. Okay, so now I'm not given any Q's. They don't just tell me, oh, this many kilojoules of heat is absorbed. They don't tell me that. Okay, so what I need to do, I need to break these Q's down into usable equations. So I'm going to take this guy, I'm going to drag him back down. All right. What's happening to my gold? Again, you ask a first grader what's happening, they'll say it's getting colder, maybe. So then I'm just changing the temperature. Because I'm only changing the temperature, I'm going to use an MCAT. So I've got don't forget that negative sign. And we have M gold, C gold, delta T gold. And what's happening to my water? It's heating up. I think. Yep. So then I'm going to have M water, C water, delta T water. Okay, I'm trying to find the specific heat of my gold, so they should give me everything else. So I've got my negative sign, mass of my gold, 40 grams. I'm looking for the C of my gold, and change in temperature, 26.2 minus 76.2 degrees Celsius. That's going to equal the mass of my water. I've got 10 grams. Specific heat of water, 4.184 joules per gram degrees Celsius. And then the change in temperature is going to be 26.2 minus 20. This would be a good time to point out, like in this problem, they don't give you the 4.184. I guess they do in part A, but they don't have to give it to you, especially on homework questions. So C values and delta H values are constant values for a given substance or a given process. And they don't change, meaning you can look them up. So if you're doing a problem and you get to this stage and they don't give you a C value or a delta H value, and it's also not what you're solving for, like in this case we're solving for that C, but if it wasn't what we were solving for and they don't give it to me, just look it up. Yeah, just look it up. We'll run into those later in the homework. So I'm going to do all this math. if I got the right answer. Yes. So I got that the specific heat of gold is going to equal 0.130, and my units are joules per gram degree Celsius. Now I'm not just saying joules per gram degree Celsius because that's what it's supposed to be. Literally over here, I've got grams that cancel grams and Celsius that cancel Celsius. So I've got joules, and I have to divide by that 40 grams, and then I divide by that change in temperature in degrees Celsius. That's how I got joules per gram degree Celsius. All right, let's keep going. All right. Most automobile engines are cooled by water circulating through them and a radiator. However, the original Volkswagen Beetle had an air-cooled engine. Why might car designers choose water over air cooling? So the purpose of coolant is to keep the engine cold, right? So we're going to want something that that is able to absorb the heat from the engine better. Well, do we have any variables that we know of that relate to how well something can absorb heat? Yes. Heat capacity, right? Heat capacity tells us how well something absorbs heat without change in temperature. And so why would you choose water? I would say water has a high heat capacity. Okay, if you used a certain amount of air and you put it around that engine, the air is going to heat up really fast and eventually be as hot as the engine. If you use the same amount of water and put it around the engine, it's going to heat up a lot slower, absorbing the same amount of heat, but it's going to heat up slower, and so it'll take a lot longer before it heats up to the temperature of the engine. By that time, you can cycle it through and cool it down. So water has a higher heat capacity, so that would make it preferable. All right, the reactor core cooling system in some nuclear power plants use liquid sodium as the coolant. Sodium has a thermal conductivity. Okay, now thermal conductivity is different than heat capacity. You can see thermal conductivity has this this time in the bottom, which is quite high compared to that of water. The respective molar heat capacities are that and that. What is the advantage of using liquid sodium over this applicant? So what's the issue that should be popping up in your head? It says this is water's molar heat capacity, which is higher than sodium's. Well, up here we said, oh, well, we'd want to use water as a coolant because it has a higher heat capacity than air. Here they're saying water has a higher heat capacity than sodium, and yet we prefer sodium. Well, what else do they tell us? They tell us about the thermal conductivity. Thermal conductivity has to do with how fast heat is transferred. So, for example, in a room where everything is the same temperature, a cloth t-shirt feels warmer than a metal pen, right? So why does a metal pen feel colder even though they're the same temperature? It's because it has a higher thermal conductivity. You touch the metal pen and it sucks the heat out of your hand faster. Heat transfers faster. It's a higher thermal conductivity. So sodium, liquid sodium has a higher thermal conductivity than water, a much higher thermal conductivity. So while it heats up more with the same amount of heat, or it changes temperature more with the same amount of heat than water does, it has a greater ability to suck heat fast. And so nuclear power plants produce a lot of heat very fast. And so if you use something with a high thermal conductivity, it might be better at pulling that heat away quickly. And you're cycling this stuff through, right? You're pumping different liquid sodium up through, so maybe the change in temperature isn't as important as the speed at which you can pull the heat out. Anyway, so just for the sake of this pulls out heat faster. Okay. All right. During a strenuous workout, an athlete generates 233 kilojoules of thermal energy. What mass of water would have to evaporate from the athlete's skin to dissipate this energy? Okay, so what are we doing? We've got a certain amount of heat that your body is generating, and you're going to sweat, and the sweat will evaporate, and we're treating the sweat as water. The sweat will evaporate. Evaporation, that's endothermic, so it's going to absorb heat. Where's it going to take the heat? From your body. So the sweat will evaporate, and that's going to dissipate the heat. We want to know how much water or how much sweat do you need to sweat off in order to take away this much heat. Well, at 233 kilojoules, I just said, what is that? That's a heat. That's a Q. Okay. They didn't tell you kilojoules per mole. They didn't tell you kilojoules per gram degree Celsius, right? That's just a heat. And we want to know how much water needs to evaporate to absorb that much heat. Well, let's break this Q down. What is the process that we're undergoing here? Okay, there's two types of processes. You could either be doing a temperature change or something that's not a temperature change. In this case, we are evaporating the water. That is not a temperature change. That is a phase change. So instead of using an MCAT, we know that Q is going to equal N delta H, and that delta H is for whatever process is going on. What process is going on here? Evaporation. So I'm going to use the Q equals N times delta H of vaporization. Well, in this problem, we know that Q is 233 kilojoules. That's going to equal N. And now I need delta H of vaporization. They don't give it to me in the problem. They do tell me there's water, though. And like I said before, if they don't give you a C value or an H value that you need, you can just look it up. So let me look that up real quick. Okay, I just found that the delta H of vaporization equals 40.7 kilojoules per mole. So if I want to vaporize 1 mole of something, it's going to take 47 kilojoules. Okay, but I'm not dealing with 1 mole. I need to figure out how many moles I'm dealing with to evaporate 233 kilojoules. So I could just say 233 kilojoules equals N times 40.7 kilojoules per mole. Okay, so I'm just going to divide 233 by 40.7, and I get that N equals 0.565 moles of, is that right? 233, oh, nope. 233 divided by 40.7, there we go. It's going to be 5.725 moles, and we're just treating this as water. Okay, and it says what mass, so I don't want moles. So if I had found a delta H of vaporization that was in kilojoules per gram, then I wouldn't have gotten moles when I divided, I would have gotten grams, I'd be done with the problem. But I got kilojoules per mole, so I get moles when I'm done with the problem, so let's change that to mass. So the mass of my water, I'm just saying 5.725 moles of water. I'm just saying I know that 1 mole of water is 18 grams. So multiply by 18, and I get 103 grams of water. So that's how much you, in theory, have to sweat off in order to absorb the 233 kilojoules of thermal energy that's produced during the workout. Okay, we're just chugging along. Let's keep it going. So, what are we doing? We're taking pure aluminum metal. We're cooling, is cooled by water from 103.2 degrees Celsius to 4.8 degrees Celsius. Specific heat of aluminum, they give you the specific heat. The water started out at 32.7 degrees Celsius. How much water is used to cool the aluminum? Okay, so set up this problem. What are my two Qs? We've got a Q for an aluminum, and then we've got a Q for a water. What's happening to the aluminum? It's cooled by water. It's just changing a temperature. Okay, so I know that I've got the mass of my aluminum, the specific heat of my aluminum, and the change in temperature of my aluminum. And those are going to equal negative the mass of my water, the specific heat of my water, and the change in temperature of my water. All right, let's plug some numbers in. Mass of my aluminum is 3.79 grams. Specific heat of my aluminum, they give it to me right here, 0.8890 joules per gram degrees Celsius. Change in temperature of my aluminum, final is 34.8 minus initial is 103.2 equals negative mass of my water. Oh, how much water is used? That's what we're looking for. Specific heat of water, 4.184 joules per gram degree Celsius. That might be a good number to know. I would hope they'd give it to you on a test, but you wouldn't necessarily have to for water. And then change in temperature of my water. Initial is 32.7, final is 34.8. All right, I can plug some numbers into my calculator. Yeah, I know I don't write down my intermediate algebra steps. If that helps you, go ahead and do it. But I just get the mass of water equals 26.3 grams. Now, there's a good chance that you do this problem and you get negative 26.3 grams. It can mean a few things. It can mean that you forgot that negative sign right there. And remember, I could put that negative sign on either side. It could also mean that you actually switch one of your final minus initial temperatures to an initial minus final. But hopefully you recognize that negative 26.3 grams doesn't make any sense, so you should use a positive value. Well, you should check your math, and then you should use a positive value. All right. Conceptual question. Why is the specific heat capacity of water so much greater than that of ice or steam? Okay, really this comes down to hydrogen bonds. Water can create a lot of hydrogen bonds and that's what kind of absorbs the heat. The heat is absorbed in those intermolecular forces, right? As you're melting something, you put in heat and it's just absorbed into those bonds. That's why it doesn't change temperature, but also even when it isn't phase changing, just changing the temperature of water, it's got a lot of hydrogen bonds that can grab and hold on to that energy. See if there's anything I'm missing here. Ice also has a lot of hydrogen bonds, but ice does not have as much translational, rotational, or vibrational motion as water does. So water has all that motion, which solid doesn't. Now gas also does have that motion, but gas doesn't have the hydrogen bonds. 3 fields of motion. Degrees is what I'm looking for, not fields. All right, how are we doing? Almost there. 2 more problems, but they each have 2 parts. Nice. Okay, so all right, an elevation where the boiling point of water is 93 degrees Celsius, 1.33 kilograms of water at 30 degrees Celsius absorbs 290 kilojoules from a mountain's climber stove. Is this amount of thermal energy sufficient to heat the water to its boiling point? Okay, so we've got water. It's 93 degrees Celsius. Excuse me, it's 30 degrees Celsius. It absorbs 290 kilojoules, and we want to know if it's going to get to 93 degrees Celsius. So there's 2 ways to calculate this. One is to use the 290 kilojoules and calculate the final temperature of the water. The second is to use this as the final temperature of the water and figure out how much heat would be required to do that. Okay, I'm going to do the first way. So 290 kilojoules, what is that? Well, that's a heat. That's a Q. Okay, so we're not doing a Q equals negative Q thing here because they give you the heat going into the water. So I know that the water is just changing temperature, so Q of my water is going to be M water, C water, delta T water. How do I know it's not phase changing? Well, it's not boiling, it's just heating it to the boiling point. Okay, so because it's not boiling, it's just heating up to the boiling point, it's still liquid, it's not phase changing. So I know that I've got 290 kilojoules equals the mass of my water. I'm going to change it quickly into grams because I know my heat capacity is 4.184 joules per gram degree Celsius. Now, could I change my heat capacity into joules per kilogram degree Celsius? Sure, but I have it off the top of my head, so I'm just going to do that. And then I'm trying to find the final temperature. And the initial temperature is 30 degrees C. Okay, so just to show you what I'm doing here, I'm because I know this algebra can be weird. I'm dividing by 1330, and I'm dividing by 4.184. So just jumping over here, I get that T final minus 30 degrees C equals, oh, I messed up. All right, where do I mess up? Currently as written, the right side of the equation is grams cancel, C cancels, I get joules. The left side I've got kilojoules. So I need to resolve that, so I'm going to resolve that by changing this to not 290 kilojoules, but 290,000 joules. Okay. All right, so what I get is that T final minus 30 degrees equals 52.11, and you can check the units, but the units are going to come out to degrees Celsius. And so then I add the 30 over to the other side, and I get 82.11 degrees Celsius. Is that correct? Yep. T final is 82.11. Is that my answer? No, because the question is this enough thermal energy to heat the water to its boiling point? Nope, it's only going to heat it to 82.11 degrees Celsius, not 93. All right, another problem. You drop exactly 10 milliliters of tap water onto a hot iron skillet whose mass is 1.2 kilograms. All of the water is converted into steam at 100 degrees Celsius. What is the change in temperature of the skillet? All right, I've got heat transferring from one thing to a different thing, so I know I'm going to have Q of my iron skillet equals negative Q of my water. They don't give me any Qs. Like in this problem, they gave me a Q. They said 290 kilojoules. They don't give me a Q in part B, so I'm just going to break these down into relevant equations. So what, first grader, is happening to my iron skillet? Well, it is cooling down. Okay, we know that because I put water on it, and the water heated up and boiled, so that means that the skillet cooled down. So I'm going to have an M iron, C iron, delta T iron is going to equal negative. What is happening to my water? Well, you'd say it's converted to steam, so it must be boiling, right? So does that mean all I'm doing is N delta H? No, I will use an N delta H, but the water started at 25 degrees Celsius and it converted to steam at 1,000. Before it could boil, it needed to heat up to 100 degrees. Okay, so my total Q of my water is going to be heating up my water and vaporizing my water. Okay. So technically I could distribute that negative to both of these, but I just put in parentheses, and I'm actually going to take that negative and put it over there. So if you remember, it doesn't matter which side the negative's on. That leaves me here. This is another situation becomes really important to put subscripts because I've got so many variables going on here. All right, let's start plugging numbers, let's make sure that I have everything I need. I'm trying to find the change in temperature of the skillet. So my goal, this is my goal. Do I have the mass of my skillet? Yes. Do I have the specific heat of my skillet? No, I don't. Remember what I told you. If they don't give you a specific heat that you need, you can just look it up. In this case, the skillet's iron, so I would just Google specific heat of iron. And when I do that, let's see real quick. There it is. I get that the specific heat of iron is 0.451, and that's in units of joules per gram degrees Celsius. Really, I found the specific heat in joules per mole degree Celsius, and then I just converted the moles to grams. All right, so now I've got specific heat of iron. Do I have the mass of my water? I have the milliliters of my water, but if you remember, for water, the density of water is 1 gram per milliliter. So 10 milliliters is the same as 10 grams. So I have the mass of my water. I know the specific heat of water. Do I know the change in temperature of my water? Yeah, because it started at 25 and it ended at 100 before it could boil. Do I know the amount of my water here? Yes. If I need it in moles, I could get it there because I have it in grams. And then delta H of vaporization, they don't give me that one. I just remember from a previous problem that I think is it 40.7? Yes. It's 40.7 kilojoules per mole is the delta H of vaporization of water. Okay, so now I have all my numbers. So, negative mass of my iron, 1200 grams. Specific heat, 451 joules per gram degree Celsius. Change in temperature, that's what I'm looking for. I then have mass of my water, 10 grams, 4.184 joules per gram degrees Celsius. Remember, I've got joules on the left, so I need joules on the right. Change in temperature of my water is 75 degrees Celsius. Get that out of the way. And now I've got to add the moles of my water is going to be my 10 grams divided by 18 grams per mole. Delta H vaporization is 40.7 kilojoules per mole. And now I've got joules and kilojoules, so I need to change this. So I'm just going to do real quickly. There's 1,000 joules in 1 kilojoule. How are we doing? Still recording? We're still recording. All right. So I'm just going to start plugging in some numbers. So let's see if I got the right answer. Yep. All right, so I plug in all those numbers, and I get that the change in temperature of my iron is equal to negative 47.5.6 degrees Celsius. Should the delta T be a negative number? Yes. Why? Well, I know that my iron's cooling down because I know that my water's heating up. So I should get a negative change in temperature of the iron. Okay, number 8. Let me grab this. Okay, chemist burns 1 mole of C2H6 in oxygen and measures that 382 kilojoules of energy is released. How many grams of C2H6 must burn to raise the temperature of 39 liters of water by 58 degrees Celsius? Assume the density of water to be 1 gram per degree or per centimeter cubed. That's 1 gram per milliliter. Centimeter cubed is the same as a milliliter. Okay, so what are we doing here? We are burning C2H6 to change the temperature of water. So we're using the heat from one thing to change the temperature of different things. So we know that we're going to have a Q, I'm going to say, of combustion because we're burning the thing. be negative Q of my water. Because all I'm doing, yeah. Okay, now I got to break these up into their respective things. Well, what's happening when I'm burning C2H6? Is that a temperature change or something else? That is something else. That's a reaction. So I'm going to use an N delta H. So Q of combustion I'm going to replace with N combustion delta H combustion. Okay, and what about my water? Negative. What's happening to my water? It's just raising the temperature. It's not boiling. It's not reacting. It's just changing the temperature. I'm using M water, C water, delta T water. All right. Do I have all these things? Do I know how much stuff I'm burning? No, that's what I'm trying to find. So that's my goal, is N of combustion. Do I know the delta H of my combustion? Well, what is the delta H, or the enthalpy, or the heat of combustion? That's defined as the amount of heat that is released when I combust 1 mole. Okay? So they could tell me in the problem, delta H of combustion equals blank kilojoules per mole. They could have told me that, but they didn't. What did they tell me? Oh, they did. They said a chemist burns 1 mole in oxygen and measures 382 kilojoules. That tells me the delta H of combustion of this thing equals 382 kilojoules per mole. The only thing I'm missing here is it says it's released, so this delta H is negative. So I do have my delta H of combustion. Do I have the mass of my water? Has the liters, and I know how to change liters to mass because they give me a density. I know the specific heat, and I know the change in temperature. So I'm looking for N combustion. I know that delta H of combustion is negative 382 kilojoules per mole equals negative mass of my water. So 39 liters, 1,000 milliliters in 1 liter, and then 1 gram in 1 milliliter. So that gives me 39,000 grams of water, 4.184 joules per gram degrees Celsius. Change in temperature, I'm raising the temperature by 58 degrees Celsius, so it's going to be a positive 58. The only problem right here is my left side of my equation is kilojoules, the right is joules, so let me just change that. I know that there's 1,000 joules in 1 kilojoule. Now let's plug in numbers. I get that I got N combustion equals 24.78 moles, but I want grams. I think, how many grams? Yep, so I've got to divide by the molar mass. Oh, I got to multiply by the molar mass. My mistake. Did I do that right? I did. All right, so the mass is going to be 744 grams of C2H6. That's the mass I need to burn in order to generate enough heat to raise water, that much water, that temperature change. Okay, last one on problem set 31. How many grams of methanol must be combusted to raise the temperature of 25 liters of water by 2.25 degrees Celsius? Give me the density. This to you should sound very similar to the last problem, like almost identical. How many grams of C2H6 must burn? How many grams of methanol must be combusted? Right. So the setup's going to be very similar. Q combustion is negative Q water. So I'm going to have an N combustion, delta H combustion equal to negative M water, C water, delta T water. Just to jump back here real quick, we added that negative from the 382 kilojoules per mole because it said it was released. If you had forgotten that, you would have gotten a mass that was negative. And hopefully that would have helped you catch your mistake. But if you're not sure how we're setting up this problem, look at the previous one. We're setting up identically. So how many grams of methanol? So we're looking for N. What's the delta H of my combustion? They don't tell it to me in the words, but they do give me the combustion reaction and tell me the delta H of that reaction. That D is just a delta. When I converted it into word, it changed it. D is just a delta. They tell me the delta H of this reaction. So does that mean that the delta H of combustion of ethanol or methanol is negative 1452 kilojoules per mole? No. It's negative 1452 kilojoules per 2 moles because I'm burning 2 moles. I want it per mole though, so I'm just going to do negative 1452 divided by 2. Sorry, negative 1452.8 divided by 2. And that gives me negative 726.4 kilojoules per mole. Methanol equals mass of water is 25,000 grams, 4.184 joules per gram degree Celsius. I want to raise the temperature 2.25 degrees Celsius. I got to fix my joule kilojoule issue. So 1,000 joules is 1 kilojoule. And I'm going to take a shot in the dark here and say that I typed something into my calculator wrong. Yes, I did. That's more like it. N combustion equals 324 moles. But I want grams, so I'm just going to say, all right, I know that for methanol, 1 mole, this is just the molar mass of the periodic table, is 32 grams. So then I get that the mass is going to be 10.4 grams of methanol. Okay, hopefully this helps you as you go back and you're working through problem set 32 again. In the next section of the video, I will be going through problem set 34.